Assalamualaikum. Bismillahirrahmanirrahim. Okay. Hi to all. This is the video for our module 5. Basically, I cannot cover all in our class, so that's why I thinking that it is good for me to just create this module 5 video. For session 9 we did some recap or touch a little bit on this module 5 before this, right, in class, but for session 3 and session 6 not yet. But don't worry, in our class I'm going to do a recap also, but not so deep. In this video is going to be full. If there is any question, it is good for you to ask me directly. Don't wait until test 2 or also final exam. Okay, as always. So what are you going to learn in our module 5 is basically related to logics, the gates and etc. Last time, if you still remember, in your module 4, mostly you are looking on the Boolean expression, the theorem, the law, the what else, rules and etc. So a lot of more to mathematical things, I guess so. But in this module 5, you're going to look into much more different, which is on visualization, which is on the second, on the logics, which is you're going to look into the gates. But last time you did look on the gates in terms of the basic gates, if you still remember. But in this in this module, it's slightly different, which is you're going to learn a combinations of N O, which is basically AND gates and O gates, and another one is N and O with the inverse, which is, what is inverse? It is a NOT gate, right? So N or inverse logic. So it is in terms of circuit basically. And then when you have this, you need to illustrate the conversion between different representations of digital circuit. After you learn last time on the basic gate, universal gate, you're going to also be introduced with universality of gates. How is it? And there is another one which is on dual symbol. It is basically your basic gate, but how to make it as a dual symbol. What is dual symbols? Is it a AND gate or OR gate or inverse gate? So what is dual symbol? Okay, then this is all objective what you're going to learn in module 5. Lastly, after you go through everything, before you after you finish all, you supposedly can explain on term of design a combination circuit. Okay, let's directly go for our first subtopic, which is a basic combination gates. Okay, first of all, you're going to look into AND OR logics. There will be a possibilities for you to be asked in the final exam, in the test 2, in terms of your lab also, which is you need to know on this basic combination logic. There is a possibilities for you to be asked, okay, draw a combinations logic only using AND OR. So you cannot have different logics, different gate and etc. So this is just a sample. AND or logic, and another one is AND or inverse. Why only these two? Because this one is basic. If you still remember, basic gates, and when it's combined together, it's going to be called as combinations logic. Okay, we go through directly on what is AND or logic. Of course, this is the symbol for AND for the gates, and this is a symbol for OR gates. When you have the combinations of AND or, you're going to have a get AND gate first. Maybe you have like two gates and two AND gates or three AND gates. This is the first phase that you're going to have. After all this AND gate, you're going to combine it together to your OR gates. You can see here. So normally this AND OR is a representation of a SOP expression. How and why I said so? Because if you see the examples expression here, you have A dot B. This is AND gate. And you have another AND gate here, which is C dot D. And it's going to be combined with the OR gate. And when you have these possibilities of SOP last time, if you still remember the SOP, you're going to have output equal to 1 if at least one of the product terms or one of the AND gate output is 1. So if you have like too many AND gates, let's say 10 AND gate, but one of the AND gate is having output of 1, your total output for your Boolean expression, which is your F, equal to be 1. So this is, you go and refer back to SOP and remember back what happened here. And in terms of visualization representation on the circuit combination, you're going to see you have AND gate here. At this part, you have 3 AND gates, and you combine it together, which add additions or OR gate. Then you are having the AND, which is this AND and OR logic. So this is the explanation. Let's say you have like 1 1 0, your output is 1 because you have at least 1 in output of AND to be 1. And if let's say you have here at least 1 also, you're going to have 1. But if you have all is 0, then it's going to be 0 for the output. This is in terms of NO logic. The representation of the expression is this example. And on the circuit, this is how it's look like. And now we're going to look into the truth table of NO gate. So NO gate, in this example, you were given that based on the truth table, please derive the expression, simplify using the CAM map, and implement using AND or logic, means that you need to draw. So the solution is, you can see here, there is the input and output of 1, output of 1, output of 1. You look into the what we can call inputs, input value. We can do it as A dot B, C dot D. But of course you can also play around with the input here. And using this, you can see this is having 1 and your output is 1, and etc. So what is the expression? So over here you can come out with the expression of A bar, B bar, C, D. That is one of the product term there. You can see A bar. Why is bar? Please remember back. If output is 1, it's going to be SOP. SOP A equal to 1, A bar equal to 0. See here? And CD. So this is one of product term. And go for another one here. You have A bar, B, C, D. Another product term is here. You have A, B bar, C, D. So let's take a look here. So this will be your standard SOP Boolean expression. After you have all these, you've been asked to do the care map. So you can draw the care map here and map the value of 1 1 here. You have 0 0 0 0 1 1, and then 0 1 1 1, and 1 0 1 1 1 0 1 1, and you continue look and map the care maps. After you map, of course you need to do a grouping. This one in our module 4. So you will get the simplification version as mentioned last time, that you will get the simplification version by using a care map. So what next? So simplify the expression using, okay, this one is, you can test this. This is basically a recap for module 4. And from here, what you need to do is, this one is using Boolean algebra, not using the care map. If using care map, we can map. But if it been asked you to do a Boolean algebra, you need to use all the rules, all the law. If you still remember that, you need to use the theorem and etc. So no need for me to like go deeper one by one. You can like go through and check the answer at the end. Try to do by yourself, because this one is from your module 4. Just a recap. Instead, what we're going to look into our module 5 is your AND or logic. So you can try to look into the answer of the simplifications. So basically it's similar. This one is using the rules and the law, and at this part is it asks you to do using a care map. And from all of this, you can see the final answer is C, D plus AB. From here, you can draw your AND OR logic. So you can get this type of circuit. that is on the AND OR logic. Now you have AND OR inverse logic. So by using AND OR inverse logic, what is the difference is from AND OR you just add another inverse there, which is your NOT GET. So the representations of this is basically you have AND OR with the bar, and this one, which is the inverse, is supposedly to be your POS expression. But how to define this? How to define that is the POS? Because you can see it is like AND. Of course, it's going to be AND first, like this, right? It's supposedly to be AND get, OR get, and OR get. So just put the bar there. This is the things which is AND OR NOT bar, AND OR, and then NOT. So this is basically what happened. But in terms of when you use the De Morgan theorem, you're going to get A B dot C D. You have what? Bar, isn't it? This is by using your De Morgan theorem. Next, you're going to have A plus B bar, and you have another one which C bar plus D bar. This is also using your De Morgan theorem. So that's why in terms of AND or inverse, it's supposedly on the expression of POS. You can see here in the picture here, you have AND O and then a NOT GET there, or it called as an inverse. So this is the expression that you will get from AND or inverse logic. But you cannot have like over bar like this. You're going to simplify it and you will get the POS expression. Next, you can see this is the example of truth table for AND or inverse. From this truth table, you need to come out with the expression. So you need to come out with the expression. And then what else you can do? Okay, if you were given with this, you can see the output is X. After that, for the output is X, it is a toggle, or it is a B, C, D bar. So from this equation, from this expression, you can get the truth table like this. When you solve this one, A bar plus B, C bar plus D, you solve this, you can map this truth table. Okay, there is another example here. Refer to the previous example, slide 12. Solve the problem for an active low output using AND or inverse logic. So you need to use the AND or inverse logic. Try to do the exercise here, which is similar, using this truth table, and you need to draw the AND or not. You can see here, you can combine it together to be the AND gate, AND gate, AND gate, AND gate, and also OR gate. After that, you're going to have a bar. To implement an active low output, so it already mentioned on active low. What is the meaning of active low? Take the complements of the X. So you can see here, you have the X bar there. This one is X because it is active low, which is a complement to each other. That's why you have the X bar. It called as a low output. If we want active low, put an inverse at the output of SOP circuit. So this is SOP circuit, which is your in or logic. If you want an active low, you have N not get or inverse there, and the combination all of this is called as N or inverse, or we can call it to put the active low, to put an active low like this using N or inverse. So you can see here is mentioned, if we want active low, put inverse, which is inverter, put inverter at the output of SOP circuit. It will produce a SOP for the X bar given. So please note that not POS for the X. X is A, B, X is here. This one is X bar. Okay. This one is SOP, and here will be your POS. Okay, this is the K map. You can map from all of these. You can map first from the truth table given. So you can see you are looking at the X bar. That's why you're going to map it using your output of 0. This is the sum of product for this group, and you're going to have another sum of product for another group. From here, you can have the expression simplification version using the K map. And after you have the simplified versions of expression, you need to draw. Implement the active low output. What is active low output? Just now I already mentioned, which is you need to add a NOT for your AND or logic by applying the AND or inverse logic. So that is the example. You can try to do it. Basically, it's similar like this. and you need to learn how to draw the circuit. Like this also, you can draw the circuit. Okay, after we done with our and or and then and or inverse logic, we're going to look into the universal property of NAND and NOR gates. If you still remember, NAND and NOR is N as a universal gates. But you're not going to learn NAND and NOR gate. Instead, you're going to learn the similarity representation for the AND gates and also NOR gates. And it will represent to the basic gates that you already learned. So if you look into this picture, it is like basically similar to your NAND gate. But what is the difference? NAND gate normally having two inputs, but here your two input are combined to be one input. It is still under NAND gate, but the input will be combined and the input will be only one there. From here, it is similar to NOT gate. So you need to remember how NAND gate can represent as a NOT or an inverse. You need to remember how your NAND gate can represent on the AND gate, and how basically your NAND gate combination can represent the OR gate and etc. So that's why here you need to memorize. In terms of NAND gate like this, you having the input 1, combine your two input, and the output is 1, you're going to have a similarity to be a NOT gate. Next, when you have two NAND gates, you combine it together, and two AND gate here use as a AND gate. Two NAND gate, you can get the similarity of the one AND gate there. You have two NAND gate, one NAND gate, two NAND gate, but you can see it's combined it together. It will be a similarity to your AND gate. You can try in your DIT simulator, try to play around with the input of like 0, 0, 0, 1, 1, 0. What is the output here? And compare, is it this output similar truth table with the AND gate? Then if correct, then you prove. But if you can't to do prove that it is similar, you need to ask me. Okay, next. When you have three NAND gate, you can construct it to be a OR gate. Okay, the question is, Doctor, why? Why you need to learn all of this? Because I already have one gate here, which is I can have OR gate. It is a situation if let's say you are having a lab, but it is a physical lab, and then you need to construct the hardware things, which is you need to play around with the gates, but it is in terms of a real hardware, not a simulator. So sometimes maybe you are having the shortage, or you are lacking on the OR gate, but you are having three AND gates. So you can use the combination like this of your NAND gate to be constructed into the circuit, and it is similar to the OR gate. So you will solve like, okay, no need for me to buy another OR gate because I didn't have OR gate. I didn't have enough of OR gate to construct my combination circuit. But instead of just waiting for buy new hardware, why don't I use existing one, which is I have 3 NAND gate. I can combine it with all my circuit to be a OR gate there. So you need to remember, okay, how the connection look like and etc. Because you will be asked to draw a circuit by using this old NAND gate. After this, you're going to learn on NOR gate. So please make sure you remember everything. You already have one NAND gate to be represented as one NOT or one inverse gate. And then when you have two NAND gate, you will get one AND gate. Another one is 3 NAND gate, you are getting 1 OR gate. And lastly, if you are having 4 NAND gates with this combination, kalau lain, or if let's say it's different from these constructions of combination circuit, then it cannot be a similarity to be your NOR gates. So please make sure you remember this representation, okay? Then you can try to use a NAND gate to implement each of the expression. So let's say I have A, which is A bar. A bar, if I still remember, this one is a NOT gate. If it is NOT gate, I need to use only NAND gate. I dah habis dah, I already finished my other gates. I only have the what we call NAND gate only. So this is my A. Sorry, it's quite ugly. I forgot to bring my pen back to my home. So here, after that, you need to have OR gate there with the B. Sorry. This OR gate. Okay. So from here, I have one, which is I will have the NAND gate there. And I have a OR gate here. You can see OR gate. So how the OR gate look like? Output. It will be plus with my B. So this will be my B, and this is my A bar. So I have so you can see here, this is the combinations of OR gate. So you have A bar, and then you're going to add, which is your OR gate. Supposedly it's going to be OR gate, but in terms of the representation, if you still remember, OR gate can be represented like this, which is similar to my ugly drawing here. This is my NAND gate combined like this. So this is my OR gate. And after this, later you're going to learn, if you have two in one line, you will remove it because it is a NOT. If not 2 times, then it will be toggle it back, right? So you can get direct input to your NAND gate here, and there is another NAND gate at this part. So the simplification versions, I guess it will be look like this. Sorry, it's direct go to the NAND gate. So this is A, this is a B. And after that, you can try to do this one. Is very simple because you have the A bar, which is you have A bar, this one is B, A, B bar, and you have AND gate. You can see here, you have AND gate there. How your AND gates look like? It will be like this. AND gate. Oh, sorry. Yes, 2. And another one. This one is A. This one is not connected. Then you have another one. So you can cancel this and this. You cannot cancel this one. So this is how basically it's look like, because you can see the input is different. So when you have like NAND in one line, you need to thinking about the cancellation between each other. So let's try to look. Okay, this is the basics gate. Now you can see this is similar what I draw, which is the NOT gate there, and this is my OR gate. So I can remove this part. See, similar to my drawing, it is directly to go there. So let's take a look into the solution number 4B. You have the NOT gate there, and then AND gate here. And for the NOT gate, this is the representation. And for the NAND gate, the AND gate here, this is how it's look like. So you cannot simplify anymore. So use NAND gate to implement this expression. So this one is very easy. You have AB plus CD. Try to do this by using only NAND gate. So you need to remember how NAND gates represent there is a bubble, okay, this one, and you need to have another. My drawing is quite ugly because I didn't bring my pen back. Okay, this one is represent as an AND gate. There is another one for another AND gate, and you need to draw a OR gate there to put here. So how it looks like this. So you can cancel after this and this and this. You can having the final answer like this. Only G1, G3, G7 left. So that is the answer. Now, just now you learned the NAND gate. Here we're going to look into the NOR gate. You can see here NOR gate. For NOR gate, it's basically similar. You can see only in term of no. Just now you are having the NAND gate. Now the no gate, if you have one no gate, it is similar to the inverter or the NOT gate. When you have two no gates, you're going to have the O gate. And third and fourth, when you have three no gate, you're going to have AND gate. And lastly, when you have four NAND gate, you can represent it as one NAND gate. Four no gates, one NAND gate. So please make sure you memorize all of this table or picture. Okay, try to implement this using only no gates. So we have a question of x bar plus b. This is the picture of the logic combinations. And when you look one by one, you have the inverter or the AND or a NOT gate here. And you represent using the only no gate. So this is the representation. After you have the NOT gate, you have the O gate. How to represent O gate in terms of no gate? So please remember back, this is how it look like for the AND gates. So this is the final answer. And now your second example, which is example 6b. You have the NOT gate there, so you can bring and label is using the NOT gate. After that, you have AND gate here in terms of representations for your NOT gate. You can see this is your NOT gate, and this is the representations of the AND gates. Okay, I forgot. You can see here and this one can cancel each other, and that is your final answer. It's quite easy, it's not too hard, but as I mentioned, you need to remember the representation. If you have one no gate, how or what is the basic logic gates that you need to have, and all this you need to memorize. So I guess for the video just now, I'm going to cut until only this subtopic or last exercise. Next, I'm going to continue with another video for a dual symbol. So thank you for watching this video. I hope that after this you directly open and watch my video for a dual symbol. So thank you and stay safe. Bye bye.